Hello, welcome to the to another module in this massive open online course. So we are looking at the problem of beamforming, that is to find the beamformer or the combiner basically which maximizes the signal to noise power ratio for the user in a particular direction, right. And we said the constraint for the signal gain, so we are looking at the beamforming problem, okay. And the constraint for the signal gain is W bar transpose H bar equals 1. This is unit gain for desired user or unit gain for signal. That is what we said the signal gain to be unity and minimize the noise power. Now coming to the noise power, the noise power can be calculated as follows. We know the noise component is W bar transpose N bar, which is basically your row vector W1, W2, WL times the column vector of noise, which is N1, N2 up to NL. So this is summation over I Wi Ni. Now we have to assume something about, we have not described properties of these noise samples, but let us assume a very commonly employed model, that is all the noise samples are statistically identical, that is they have 0 mean and variance, that is expected value of Ni square equals sigma square, that is noise samples are variance of power, the noise power is sigma square, okay. And they are 0 mean, these noise samples Ni are 0 mean, okay. And in addition, let us also assume that if you take two distinct noise samples, expected value of Ni times Nj, this is equal to 0, that is if I not equal to j, that is the distinct noise samples, the different noise samples are uncorrelated. Uncorrelated noise samples. In addition, if these are Gaussian, if Ni are Gaussian, then uncorrelated implies that they are also independent. However, this does not hold for non-Gaussian noise samples. Typically, the Gaussian samples are assumed to be additive white Gaussian, which means that the different noise samples at the different antennas are independent and identically distributed. Identically distributed in the sense that they have 0 mean and identical variance sigma square. So we say the noise samples Ni are Id equals independent identically independent and identically distributed, okay. Now if you look at the noise power, that is expected value of summation over I Wi Ni square, this becomes expected value of, I can write it as a quantity times itself Wi Ni times summation over j Wj Nj, which is equal to the expected value of, well, multiplying it out, summation I summation j Wi Wj Ni Nj, and now it is easy to see what this reduces to. So take the expected value inside, summation over Ij expected value of Wi, Wj, Ni. In fact, Wi, Wj are constant, so you can simply write this as Wi, Wj expected value of Ni and j. And we have seen this is equal to 0 if I is not equal to j, and equal to sigma square if and only if I is equal to j. Okay. So, only the term, so when I is not equal to j, expected value of Ni Nj is basically 0. The noise samples on the two different antennas are uncorrelated, alright. So, only the terms where I equal to j survive, and therefore, I can simplify this as, since only terms where I equal to j survive, and in that case expected value of Ni Nj is sigma square. So, this will be I sigma square, when I equal to j, Wi into Wj will be Wi square. So, sigma square summation Wi square, taking the sigma square outside, this will be sigma square summation Wi square, which is basically nothing but norm W bar square, and this is basically your noise power. This is basically the noise power. Okay. And therefore, now I can formulate my optimization problem. Now, my optimization problem will be the following. The optimization problem remember, the optimization problem for beamforming is to minimize the noise power. We have just found the noise power, that is minimize sigma square norm W bar square. That is, what are you doing? You are minimizing the noise power. Minimizing the noise power subject to the constraint W bar transpose H bar equal to 1, that is your signal gain equals constant. Or constant gain in the direction of desired use. So, what you are doing is you are minimizing the noise power, keeping constant signal power. So, what does is that maximizes the signal to noise power ratio, that is what we said. Okay. And therefore, if you look at this optimization problem, it has two parts. First, what you are trying to minimize, this is termed as the objective or the optimization objective. Or simply the objective function, and this is termed as the constraint, because remember we have to ensure W bar transpose H bar equals 1. This is termed a constraint, or in fact you can have more than one constraint, you can have constraints. Okay. And if you see, this constraint is an affine constraint. It is an affine equality constraint, and if you look at the objective is convex. Where sigma square norm W bar square. Well, minimizing sigma square norm W bar square, this is equivalent to minimizing norm W bar square, because sigma square is a constant. So, if I minimize norm W bar square, I will also minimize sigma square norm W bar square. And now look at this, norm W bar square is simply W1 square plus so on WL square, sum of convex functions. So, this is a convex objective. Affine constraint is also a convex constraint. So, you have a convex objective function and you have a convex constraint. You can have more than one convex constraint, you can have a set of convex constraints. So, convex objective, plus convex constraints. That makes a convex optimization problem. That is a special subclass of optimization problems which we are going to focus on. So, this is going to be the template of a convex optimization problem. So, convex objective plus convex constraints implies a convex optimization problem. So, this implies convex. So, we have a convex objective, we have convex constraints. This implies we have a convex optimization problem. So, in fact, we have a constrained convex optimization problem. Constraints are an implicit part. I mean, constraints are, this is the part. So, this is, you have an objective function and not just the objective function, but you also have a set of constraints that the desired solution has to satisfy. How do we solve this? Let us formulate the objective part. Let me rewrite the optimization problem. So, I am dropping the sigma square because it is a constant. So, I am going to simply minimize norm w bar square subject to the constraint w bar transpose h bar equals 1. What I am now going to do is something that you must have seen in an early course on calculus, that is to solve a constrained optimization problem, one needs to use Lagrange multiplier. So, I am going to form, and by the way, this is equal to norm w bar square equals w bar transpose w bar n, which is basically f. I can denote this as w bar transpose w bar plus lambda times 1 minus w bar transpose h bar. Okay. And now what? So, this quantity lambda, this is the Lagrange multiplier. This is the Lagrange multiplier. Okay. And this has to also, this is a new parameter in the optimization problem, and this Lagrange multiplier also has to be determined as the solution to the optimization problem. Okay. So, now I am going to differentiate this with respect to w bar and set it equal to 0. And that gives us w bar transpose w bar, differentiate that gives us 2 w bar plus lambda time differentiate 1, that gives 0, minus differentiate w bar transpose h bar, derivative of that is h bar. So, set it equal to 0. So, this implies 2 w bar equals lambda h bar, which implies w bar equals lambda over 2 h bar, that is w bar equals lambda over 2 times h bar. Okay. And this is the optimal beamformer. Why is it the optimal beamformer? Because it maximizes the signal to noise power ratio. Maximizes the signal to noise, and you can see that the optimal beamformer is proportional to h bar. So, therefore, this is also like a matched filter. In fact, this is a spatially matched filter in space, right, because typically you have a matched filter in time, this is a matched filter across the antennas, correct. So, it is a spatially matched filter. So, w bar is proportional to h bar, which implies that this is an analogous to a matched filter that you employ in a digital communication system. Now, how do we determine lambda to determine lambda, this Lagrange multiplier, we have to use the constraint. What is the constraint? Remember, the constraint is WR transpose H bar equals 1. Substitute the value of W bar, that is lambda by 2 H bar transpose H bar equals 1, which implies that lambda by 2 H bar transpose H bar equals lambda by 2 norm H bar square equals 1, which implies lambda equals 2 over norm H bar square. So, lambda equals 2 over norm H bar square, correct, okay, and that is what we have, and therefore implies the optimal beamformer, which you can now denote as W star. W star equals, well, lambda by 2, so that is half lambda 2 over norm H bar square into H bar, lambda by 2 into H bar. So, this is H bar divided by norm of H bar square. So, this is your optimal beamformer. So, this is the optimal beamformer, H bar divided by this is also termed as the maximal ratio combiner, because this maximizes the signal to noise power ratio. It is also termed as the maximal ratio combiner. Okay. So, this is also termed as the okay. So, that gives us the optimal beamformer, which is H bar divided by norm H bar square, that is a maximal ratio combiner, and this maximizes the, it is known as the maximal ratio combiner because it maximizes the SNR, correct, maximizes the SNR employing the beamforming. Maximizes the SNR at the output of the beamformer. And what is the SNR? That is easy to see. If you have y bar equals H bar times x plus n bar, let this be P, symbol power equals P, that is expected value of x square, okay, symbol power equals P. Okay. And now what am I doing? I am beamforming with the maximal ratio combiner, that is H bar transpose divided by norm H bar square into y bar. Remember, this is a maximal ratio combiner, which is H bar transpose H bar divided by norm H bar square times x plus H bar transpose n bar divided by norm H bar square. Now, if you see this H bar transpose H bar, that is norm H bar square divided by norm H bar square, which is 1, and that is indeed true because we ensured that the signal gain is 1. So, this is H plus H bar transpose n bar divided by norm H bar square. Therefore, the SNR at the output of the maximal ratio combiner is simply signal power, that is expected value of x square by noise power, but we know noise power is sigma square times norm W bar square. We have already derived that for any combiner. So, expected x square is P divided by sigma square, norm W bar square, remember W bar equals H bar by norm H bar square. Norm W bar square is norm H bar square divided by norm H bar power 4 equals P divided by sigma square into norm H bar square. So, the SNR at the output is norm H bar square into P divided by sigma square. You can also write this as norm H bar square into rho, where rho equals P divided by rho equals the transmit. So, P equals the symbol power sigma square equals noise power and rho equals P divided signal power by noise power. You can think of this as the transmit power, because this is the power of the transmitted symbols. Okay. So, rho equals I am sorry, transmit SNR P over sigma square, which is the transmit SNR. Okay. So this is the interesting thing. So, this is the first convex optimization problem, which is a rather simple application of the optimization framework which we have seen, and you can clearly see it is very powerful and very handy, right. You can formulate a neat optimization problem wherein you are trying to design the optimal beamformer. You set the beamforming gain or the gain of the beamformer in the desired direction and the direction of the signal to be unity. That gives you your constraint, and you minimize the noise power, which is sigma square norm W bar square, to basically essentially maximize the signal to noise power ratio. We used the Lagrange multiplier framework to formulate the Lagrangian basically differentiated set equal to 0. This is also known as the KKT framework. We will look at it in more detail as we go in the subsequent modules, but initially this illustrates to you in a very simple fashion through a practical example how the optimization framework and more specifically the convex optimization framework can be used to solve practical problems. Alright, so we will stop here and continue in the subsequent modules.